Hi POE students, I'm going to walk you through the formulas and some relationships that deal with stress and strain. Okay, so we are, just to provide some context, we're talking about material testing and we're talking about tensile strength. So we are talking about putting a force on material such that we create tension. So that's a pulling effect. Okay, so imagine a material where we're testing and we're pulling with force to see what the relationship is here between force and really stretch, or we might call elongation. And so we get a graph if we plot two things, force and how much this material stretches, which is going to be elongation. It's delta. It's a lowercase Greek letter delta. And you're going to get a graph that looks something like this. Okay, and we've already spent some time in class discussing this, but I'll remind you real quick that this linear section is called the elastic region. This is the region where the material will go back to its original length, okay, if we release the force, release the tension. Once we go beyond that, we get to a yield point where the material has deformed to a point that will never go back to its original length. And really we've begun, the material's begun to fail. At this point, at the peak, the highest peak, we would find the material's ultimate strength. And beyond that, you can see that we get more stretching, elongation. So we continue to get stretching even as we back down on the force. So it's really in kind of complete failure and then it breaks. So we've got this relationship. Force, the amount of force and the amount of stretch can depend on the size of our sample. And so we want to remove the sample size as a variable or something that relates to our graph or can affect our data. And so we are going to transfer force and elongation into stress and strain. Okay, and so for stress we have the sigma, and strain we have this epsilon. And so we're going to have the same shape graph, but we will have removed the variable of what our sample size was. How we do that? Well, stress, so here's some of your formulas, relationships. Stress is force divided by area, and that area is the cross-sectional area. So if you were to essentially create a section view, kind of a slicing plane here, what's the area of the cross-section of that material? So force divided by the area of the cross-section will give you stress. Strain is the amount of elongation we got divided by the length of our sample piece. Okay, so this is elongation divided by the original length, and that's strain. Now, you may remember that in class earlier we talked about the modulus of elasticity, a material property that has to do with how much the material might, how stiff it might be. So as we started looking at this graph, modulus of elasticity, or E, is the slope of the elastic region. And if you remember from math class, slope is rise over run. And whether I take a big stair step or a little stair, it's the ratio, the rise over the run. And as long as this is linear, the ratios of these should be equal. So we say it's proportional. We also refer to this, or at least kind of where this linear section of our graph stops, as the proportional limit, because along here it's proportional. We have equal ratios. And so modulus of elasticity is really the slope of that, and this, the rise, okay, I really should be over on this graph, I guess, is the stress. And the run, well, that's the strain. Okay, so modulus of elasticity. My classroom lights just turned off because I'm not moving enough. Okay, another formula we have, and I'll derive it for you in a second. It's kind of been manipulated, but it's another way to show a relationship with elongation. So how much the material stretched. Elongation is equal to the force times the original length divided by the cross-sectional area times the modulus of elasticity. And this is actually derived from the above three formulas. This is a useful relationship in that we've got 5 different variables in one equation, and if we perhaps can have 4 out of the 5 that are represented here, we can solve for the missing piece. So where does this come from? Well, it really comes from the modulus of elasticity relationship being sigma stress over strain. Okay, and stress and strain have been defined over here. So if we make a substitution and we replace stress with what stress is equal to, force over area, and then in the denominator we replace strain with what strain is equal to, and that is the elongation over the original length, you can see that we now have 5 variables in one equation, and it's just a little manipulation, a little algebra to go from here to here. Okay, so that's where that comes from. I'll go ahead and show it if you're curious, but that right there is kind of, in a nutshell where we get that. Okay, and hopefully that makes sense. Here it's just algebra to kind of prove, how this equation's been laid out. So for those of you that are curious, what we do is we rewrite a fraction divided by a fraction. That's not very pretty to have a fractions instead of fraction. And a fraction divided by fraction is really multiplying by the reciprocal. So we flip that. So the reciprocal of the denominator is the original length over the elongation. And we can rewrite that as just one fraction now. Multiplying fractions, we go straight across. And you can see we're getting closer. But at this point, we've manipulated it so that elongation's been solved for. So I would multiply both sides by the elongation, okay, to get that to cancel. And then I would divide by, if I have another color to use, pen, no, maybe black. Oh, that's red. Okay, well, I would divide, since I'm trying to solve for elongation, divide both sides by the modulus of elasticity to get that to cancel. And over here, dividing is simply putting it in the denominator instead of the numerator. And so you can see now we end up with the elongation of the material is equal to force times original length over cross-sectional area times modulus of elasticity. So that's where that comes from. But there you go. So those are your stress-strain formulas. The one in there that is going to change a little bit is capital A, the area. So just do note that you may need some area formulas. And common ones would be, a rectangle, length times width. That one gets used a lot. And the other common one here is pi r squared, which is the area of a circle. And some people will even rewrite that, and they will say, well, you know what? A radius is actually half a diameter. And so they'll write that area of a circle formula with diameter instead of r. So really, if we replace r with 1/2 d, or d over 2, same thing. Okay, so there's pi, that's really r squared. They will rewrite this as pi. I don't know, I've seen it different ways, but you got to square both the d and the 1/2, so kind of d squared over 4, kind of 1/4 d squared. Some variation of that, they'll have it. Same thing. So we've got area of a circle is pi r squared. You might come across sometimes where it's been written this way, and they just simply said, hey, the radius is half a diameter. Okay. All right, so these are going to be your tools to solve our stress strain calculations for activity 2.3. Good luck on those.